Okay, hi everyone. So let's discuss now the the successive relaxation method. So as we discussed last time, the Gauss Jacobi, we just used the old values from the previous iteration. For the Gauss Seidel, we utilize the most recent available values for the approximations. And now the successive relaxation will have this relationship, no? So the value of your present approximation for a certain what do you call this? For a certain unknown. So instead of having just either the previous, no, or the most available new one, we can present this lambda and 1 minus lambda per equation. If we utilize this, as you can see, if lambda is equal to 0, so if this is equal to 0, this will cancel out, ano? And this will also cancel out. So the new approximation will be just from the old values of the approximation. But if lambda is equal to 1, if lambda is equal to 1, this will remain, and this will be 1 minus 1, which is equal to 0. So this will be cancel out. So the approximation of your variable will be this, no? But for if we turn this knob, no, so you can think of lambda as a knob that you can turn if you want to have some flexibility in finding the solution. No? So usually utilize the over relaxation. So lambda is usually in between 1 and 2. Okay? So the domain of the lambda should be in between 0 and 2. Okay, so remember this. So if lambda is equal to 0, it is Gauss Jacobi. If lambda is equal to 1, then it is Gauss Seidel. And then actually it should be less than or equal to ano for for under relaxation in between 0 and 1, over relaxation 1 to 2. So let's have an example utilizing successive relaxation. So solve the system with Gauss Seidel using over relaxation. Lambda is 1.2. So again, Gauss Seidel has a variant of the successive relaxation. We can have a value of lambda as this. So now we have a stopping criterion as a percentage. So how does this work now? No? All right. So again, we will check for diagonal dominance. So don't forget the diagonal dominance. So as you can see here, so is 3 greater than 12. So no, ano? Is 2 greater than 10. So no. So as you can see, this is not diagonal dominant. No. So we have to interchange this to establish diagonal dominance. So this will become 10x1 minus 2x2 is equal to 8. And then we have 3x1 plus 12x2. Sorry, this should be negative, no? 12x2 is equal to 9. So as you can see, comparing this to the other coefficients of the other row or the other elements of the row, so 10 is greater than or equal to the positive 2, no? 12 is greater than or equal to 3. So it is already diagonal dominant. We can guarantee the solution. So after doing that, we can formulate now the values of x1 and x2. So for x1, what is the value of x1? So we have this. So we have 8 minus, or sorry, plus 2x2 all over 10. And then for x2, we have 9 minus 12x2 all over negative 3. Okay, so we can actually simplify this if you want to make things easier for us. No? So we have here x1 is equal to 0.8, right? Plus 0.2 x2. Diba? And then for x2, this is equal to, we have here negative 3 plus 4x. This should be x1, ano? 4x1. Okay, so we have this iterative scheme. So again, x sub 2 here is the previous one since we do not have an approximation for that. So x1 is the previous one. So the furthest available, we can just utilize this as this. So this should be x of 1 raised to k. No, not really the power of k, no, but the iteration counter. And then this will be x of 2 k. Okay, now, so what should we do here? Hmm? What shall we do here? No? So again, we have the new x new of I is equal to lambda x nu, okay, plus 1 minus lambda x old. So what does this mean? So let's say x1, for computing x1, we will add here a new formula that we should utilize to get x sub k. So for this one, we have, I think it will not fit there anymore. So for x1, we will update this x1 again. We will update the x sub 1 again by using this. So we have lambda as 1.2. So we will multiply this 1 by 1.2, 1.2 of this current x of 1 raised to k. I'll just call this, I think apostrophe na lang, 1.2 x sub 1 nu or k. And then plus, so we have 1 minus 1.2. So if lambda, it should be negative, no? So negative 0.2 old, no? So we have x1 and then k minus 1. So we will utilize this. After we solve for this, we will utilize this one as well. And then for x sub 2, so of the iteration scheme, we have here 1.2 x sub 2 k minus, again, so 1 minus 1.2, this will be negative 0.2, and then x2, and then this will be the previous one. So we will utilize this later as well for solving our system. So for the first iteration, I guess it will not fit here anymore, but let's try. So for the k or the iteration counter, okay, and then we have x1, we have x2, and then we have to also solve for the approximate error. So meaning this is just the approximate error, guys, no? So what does S mean? So the solution set, no? So X here, or sorry, this is also the relative error, or to be exact, the percent relative error. So we have the percent relative error for the one, no? So absolute value, and for two. So the first iteration, since we do not have a given, we assume that the value of this is equal to 0. So we have 0 here, and then 0 here, 0 here. So we do not have here an iteration. So blank, leave it blank. So for k is equal to 1, we can now solve for x of 1 sa calculator. So for the formula f x of 1, we have, actually you can change this one, no? But anyways, yeah, let's calculate this anyway. This will be longer than usual, So we have 0.8 plus 0.2. We don't have a point here. So 0.2 x sub 2. So calc alpha x sub 2. So we have b. I'll just notate this as a and b nga pala, no? A and b. Okay. So we have to use calc. So b is 0. So the first solution is 4 over 5. So 4 over 5 is the calculated, but we will use this. No, don't forget to use this. Okay, so we have the relaxation. So this two equations is the relaxation. The relaxation portion of the method. Relaxation. Relaxation. Yeah. So this 0.8 will now be substituted here, and then we will utilize the previous value of this. So we have 1.2, and then we have alpha A, okay, and then minus 0.2 times the previous one, no? So I'll just put here C for the previous value of x of 1. So calculate this. So we have the current approximation is 0.8, and then C here is 0. So we have here 0.96. So the answer here is 0.96 for the first approximation, ano, of x sub 1. Let me just check. Let me just check this. Okay, we're correct. No? And then for x sub 2, where is the calculator? And for x sub 2, we will utilize this again. So x sub 2, we have x sub 2, so we have -3 plus 4 alpha a. So calc this, and what is the most recent value of a? So 0.96. Okay, so the answer is 0.84. So this is not yet the final answer, ano? So 0.84, after you do that, you will now substitute the value of 0.84 here. So 0.84, so 1.2, I guess we will utilize this one. I'll change the notation here, no? So I guess, I don't know, no? Might be confusing. But anyway, sige, let's try. We're trying as we go, no? We're trying to formulate a new method or a new calculator technique as we go on. So the C here is equal to, so we have 0.84, we calculated this already. So the previous one is 0. So we have 1.008, no? So let me just check here. Just checking if this is correct. Oh, where did I go wrong? Recalc 0.96. Um, I think I have a formula wrong, no? It should be 12. Oh, I got this wrong, ano? Okay, sorry guys. So this should be 9 minus 3 pala, no? Plus 3. And then over 12. Ayan. Oh, sorry, sorry, sorry. So that is why I am wrong. Okay, sige, let's change this up. We have 0.75, and then this will be 0.25. Oh, anyways, yeah. Okay, so we have A here. Okay, let's go back again to the formulation. So we have 0.75 plus 0.25, and then alpha A. So calculate 0.96. So the answer is 0.99. So 0.99, we will substitute this to our formula. So 0.99 to this. So 0.99, sorry, not that one. Calc and then 0.99 for C, and then D is just 0. So this will be 1.188. Okay, this should be zeros here. And then for the relative error, so we don't have yet a value here since okay, we don't have a value here yet. We'll calculate the first error as we have a new non-zero solution. Ano? So for number 2, let's do this again. So 0.8 plus 0.2 x2. Let's see if we still have this. So 0.8 plus 0.2b. So b here is the most recent one. So we will input here 1.188. The answer is 1.0376, right? No? But this is not the answer, no? Sorry, I wrote this down. But we will utilize this. We can save this, no, if you want. But I guess I will just remember this. And I will input this here. So we have here calculate, and the C here is 1.0376. And then the D here is, so the previous one is 0.96. So the new answer is 1.0351. Ano? 1.05, 1.0531 pala, no? So the answer here should be 1.0531. And then for x2, So we will do this again. As you can see, it is cumbersome to solve this. There's a lot of computation. So the most recent value of A for x of 2, we have 1.0531. Okay, and then the value is 1.0133. You can actually write this down as you go now so that you won't lose it. You can organize your tables efficiently. If you try writing here 1.0133, and then I will write here, I guess I will just write this down so we won't get lost. 1 point, so just a note here, no? So this is, I think this is 0.84. Oh, sorry, 0.8. 0.8, this is 0.99. Okay, so that we have notation, no? Okay, so again, relaxation. So we have this. So calc C. So what should we have for C? We have 1.0133. And the previous approximation is 1.188. So we have 0.9784. So 0.9784. So let me just see if I'm correct in my notes. Just checking, no? Oh, okay. Hmm. What is that? Okay, let me just check again. 133. Okay, and then this. Okay, very good pala, no? Very good. So we are good now, no? For this one, as you can see. And we can now calculate the relative errors as soon as we have two successive non-zero values. So how do we solve this? I think we can solve this. We can create another formula. So we are using a lot of formulas here. So I'll just use F and E, and then over alpha F, alpha F, and then times 100. Okay, sorry. Calculator pala to, no? So F is the present, E is the previous. So F, we have 9.9784. And then we have, so we got this one. No? We start with X1 first. Oh, oh, nawala. Sorry, sorry, sorry. Okay, so F here, so for X1, we have 1.053, 1 and 0.96. So we have 8.84%, 8.8406%. And then for the next one, we have calculate this as 0.9784 and 1.188. So you have negative 21, so this will become positive 21. So 21.4227%. Okay, so we will move on to the next one. Since, okay, we are good with this one, but since the second solution, no, so x of 2 is not yet less than or equal to 10%, therefore we should continue doing this. So for the next one, let's go back again and utilize this formula again, and then this one after that. It is pretty exhaustive, ano? So calculate this. So the most recent approximation is 0.9784. And then the value of your x1 is 0.9957. 9957. Sorry, this is not the answer. So 0.9957 here. And then you will use thus the relaxation. Ano? So the relaxation, we will utilize this. So calc, so the most. So we have 0.9957 for the new value, and D is 1.0531. So 0.9842, so 0.9842. And then for x of 2, so we have the other formula. Okay, so A here is the most recent value of x of 1, so 0.9844. So we have 0.961, and then we will relax, no? It is not relaxing to do this. So 0.9961 minus, so D here is 0.9784, so the previous value. So 0.999966. Ayan. Let me just check if I'm correct. Just looking here. I'm just cheating, no? Okay, let's see. Ayan. Okay, I'm correct. Okay. So let's check now the approximate errors. So we have the other formula. So calc. So the present for x of 1, we have 0.9842 and 1.0531. Yeah. Okay, so we have 7%. So 7.006%. And then for 2, x of 2, we have 0.9996 and then 0.974. So this is 2.12%. So what can we say? This is already your solution. So as we can see, this already the stopping criteria is met. So this is less than or equal to 10% for both. Therefore, the solution for x1 and x2 is equal to this, ano? And then for x2, we have this. Okay? So that is all for successive relaxation. So as you can see, this will be troublesome if we have a 3 by 3 successive relaxation. We have a lot of things to consider. So this is easier, or a computer will do this much more efficiently and much faster than we can do. And they won't be prone to blunders that like what I do, no? They have some blunders here and there. So you have to be really careful. So to really understand this, you have to practice your solution. No? O sige, so for the last portions of this, I just want to summarize everything that we have learned so far. So regarding the iterative methods, comparing the Gauss-Seidel and the Gauss-Jacobi, so we have here somewhat a figure to represent the Gauss-Seidel and the Gauss-Jacobi iterations. So for the Gauss-Seidel, which is letter A, so as soon as the x1 is available, and also as you can see here, as soon as x1 is available, you will use this for your iteration. So as soon as x2 is available, you will use this as well. Ano? So that is the Gauss-Seidel. But for the Gauss-Jacobi, it is a little bit slower because the x2 and x3 is not yet updated, no, and the x1, x2, and x3 is not yet updated. After you finish one or a set of equation, that is the time that you will use that for the second iteration. Okay, so comparing this to the direct method, okay, usually if we have the if our equations on the right hand side or on the left hand side is constant, meaning if A matrix is constant and only B is changing, so what is that? So from your linear equation AX is equal to B, if only B is changing, A is constant here, then it is much more useful to use direct methods. You know? So otherwise, you should use indirect methods or iterative methods. And comparing Gauss-Seidel and Gauss-Jacobi, Gauss-Seidel will converge much faster compared to the Gauss-Jacobi, assuming it is diagonally dominant. And another thing to mention here is the round of errors. No? So round of errors, iterative methods. So one important property of iterative methods is that even though we have rounding errors, it is self-correcting. Self-correcting. So even if you make a mistake it will correct itself even if there is a blunder, as long as your algorithm is correct. Even if you have if you misread, let's say 6 to 9, it will still self-correct. Comparing this to direct methods, it will be highly prone to round of error. Okay? Yan. So, for the most part, it is still more practical, no? Usually, we should use iterative methods for solving system of linear equations as long as it is diagonally dominant. Okay? That is basically what I'm saying here. But direct methods are still useful, and as long as we have a good precision, if as long as we utilize pivoting, scaling, ano, and higher precision of storage of data, then direct method will still be a good method to use. Okay? So that is all. So good luck, guys, and thank you for listening.